We are about to start. Okay. Everyone bring calculator? Yes? You have calculator? Take it out. Calculator. Okay. Who has the calculator that? Oh, right now it's 11 already. Okay. 11:08. We are a little bit late. So who thinks you don't have calculator that is good enough? Any calculator that doesn't work? Oh, announcement first. I forget. Tomorrow at 4 to 5 session. There's another professor scheduled the room at the same time for 201. We may have to move it to next week for just 4 to 5 session. Okay, not 1 to 2 to 3. But you want to move the whole thing or what? So only the case where we have the conflict. Okay, that is 4 to 5 session. Rohan and Rawal, is that okay with you? Sure. Okay, let me. Rohan, Simon, Forrest, Ryan, Benedict, Stuart, Richard, blah, blah, blah. Those who in 4 to 5 session. Are you all here? Who don't want to move to the next week? For those who are in 4 to 5 session. Stand up. Stand up. Stand up. Who else? 2, okay. It's okay to stand up. It's nothing wrong, okay? But please stand up, okay? 3. Yeah, we will talk about that. So who else? We have to move like 4. Stand up. What? Can you say that again?
Can you record it? I'll watch it on YouTube.
Right now?
Or later.
Yes, the lab will be recorded. Okay, the first one. So just to you, you stand up too, right? Keep standing up, okay? Okay, keep standing up. Okay, Simon, you don't want to move to next time. How may I help you? When do you want to do it?
How about 1 o'clock?
1 o'clock? I will think about it. What about you? So when would you like to do it? 1 o'clock? 2 o'clock? Oh, 1 o'clock also work for you? Okay. What about you? What's your name? Eric. When do you want to do it? 1 or 2. How about if it is okay, could you please do at 2 p.m. and 2 of you do at 1 p.m.? Is that good? And we don't have 4 to 5 sessions. Where's Mattel? Can you do next week 4 to 5? You can, right? You will. All right. So the rest, please sit down. Thank you very much. So the rest of those who are in session 4 to 5, we will do it 4 to 5 p.m. but next week. Good? Who just come in? What's your name? What's his name? Are you in 4 to 5 sessions? Yes. Is it okay to do 4 to 5 next week? Yes. So next we will talk about quiz today. We will have quiz, right? That's why you have calculator. But I would like to make sure that everyone can do it. Okay. The quiz is about calculate friction factor from the. Bring your calculator. It's about calculate friction factor from Colebrook-White equation. Okay, and we will do the quiz at the end. Okay, we will do the quiz at the end. But right now, we want to make sure that all of you can do it first. Are you ready for that? Okay, whose calculator doesn't seem to work well? Whose calculator doesn't seem to work well? Basma, come to the podium, please. I didn't bring the calculator. All of you bring it, but I didn't bring the calculator. Okay. Last time I understand that we we go over it pretty quick, right? Not all you be able to do it. But this time, we make sure that all you can do it. You see the equation. Let me bring this quiz thing. Okay, we are going to solve this equation. Dot can 1. Yes.
This gonna be on the quiz?
What?
Is this on the quiz?
It is. Yes, of course. Yes, of course. And the paper. Okay, this thing that you are seeing right now is part of the quiz. Okay. Coburg White for finding friction factor is given like that. Okay. The rest I don't tell you, but you know, it is just epsilon d. You cannot see it, Rohan?
Yeah, could you zoom in, please?
Come to sit next to Steven. Come here. Sit next to Steven. There's one more seat over there, right? Come. You sit back there, you won't see it. Okay. I'll zoom in a little bit more. Okay. Alright. Is it better? We are going to solve for that. And to solve for that, so step 1, you need to have ANS. Okay, ANS. So ANS is previous answer.
You gotta turn the light on.
Turn the light on.
Yeah.
Like this. Okay. Let's do the case where we match the example so we know whether we do it right or not. Okay. So in this example, we have epsilon is 150. Right? Reynolds number is 10 to the power 5. Okay. ID is 0.052. This is an example. Example won't match the quiz, but it's close. Okay. So make sure you can do it. The equation is the implicit form, right? That's the equation, it's implicit form. We try to solve for friction factor, finding friction factor. So step 1, we need initial guess. So what I put is 0. Your calculator doesn't have any number over here. 0. Point, where's point? Is this one? Okay. Point 0, 1. And I press, is this a 1? EXE, right? Yeah. So now I get that. So this is to put it on the memory. If I do shift, I don't need to do shift. If I do answer, I press it again, it tells me the previous value. All you have that, very easy, right? How do I make it show like 0.01 instead of 1/100? Okay, now I get 0.01. Alright. So next step is, you see the equation in the middle screen? F equal to the whole thing to the power of -2. Okay, I think my hand is shaking. So we have to put all that in. Step number 1, we put parentheses. Where's the parentheses? Is that parentheses? Okay, parentheses. Minus, where's minus sign? You have parentheses minus 4, right? Okay. And we put multiply log base 10. Log base 10 is that. Okay, I have log base 10. Epsilon over D. So epsilon is micrometer, right? Basically that is 150 to the power 10 to the power of -6. So it is 0. Let's put 150 E. Okay, E -6. -6. Okay, I do that, right? Divided by D. D is 0.052. 0.052. See that? Okay, now divided by 3.7 divided by 3.7. Okay. Plus 1.256. Okay. Divided by Reynolds number. Reynolds number is 1E5, right? 10 to the power of 5. So we put 1 E. If you don't have E, some calculator has E instead of this button, okay? E5, right? 1E5. And then divided by, okay, square root F. Okay, square root and F, okay. Now it's a trick. Instead of F, we put A and S, answer. We put answer over there, okay? Then we close parentheses for log. Oh. So I go outside, we put parentheses for log. I check my formula, did I do it right? They put parentheses before log. Yes, I have parentheses before log. I put parentheses, one parenthesis for log. Oh. And another parenthesis to close everything, right, at the back. And raised to the power of, raised to the power of, raised to the power of minus 2. Minus 2. After I put everything in, now in the quiz, you don't have to put formula, you don't have to put anything, but you have to show the value from each iteration. Write it down. So my job is I press EXE. That button EXE. I know that it doesn't have anything over there, but it's EXE. I press it. Okay. I get 6.748 times 10 to the power of minus 3, right? And it matched to the first answer. Okay, I press it again. I get the second value. I write that down. I press it again. I write that down. I press it again. I write that down. I keep pressing EXE. That's it. Until it's converged. Okay, so I write number from each iteration down. Okay, that's it. 10 points for the quiz. But of course, for the quiz, it will be different. I know that not all of you can do it at home or even get help from Aya or anything. So, good? Or you need this, need cover. Who cannot do it? Who cannot do it? Okay, let's try. You have to get something similar or identical, not similar. Oh. Sometimes you get error message. Who get error message? Raise your hand. Oh, you can do it? Cannot believe that. Typically, it's required like 10 more minutes after the first explanation. Steven, you good? Tristan, you know it's not a group project, right? Each of them has to test and have it in their calculator. You finished? Or you not? You finished? In the quiz, it will be for some other value. Okay? Who haven't finished it yet? Tell me. Okay, one. Who else? Did you finish the successive method? You get the right answer. If your value is correct, you get 0.006804747. Do you get that? If you don't get that, it's wrong. It's 0. It's either 0 or 10. Okay? Who haven't finished it yet? Everyone finish it? I think you may need help. Muhammad. Is that Muhammad? Behind you? You finish it? Yeah?
Yes.
Finish it? Victor, you done?
Yeah.
Everyone done? Taylor, Cooper, you done? Good? It is on the quiz, okay? Paul, yes. Good? It has to be identical. I think your screen is brighter. Is it brighter? I have to tilt it anyway. So I do parentheses. Minus sign, where's your minus sign? Minus 4 multiplied by log log, where's log? Okay, log base 10 epsilon 150, where's E? Okay, capital E. E minus 6. Minus 6. 6 is right there. Divided by 0.052. Right? Divided by 3.7. Okay, good. You good at this part? Plus 1.256. Divided by RE 1E5, right? 1E5. Divided by square root. Where's your square root? This one, okay. Square root answer. Okay. And move one outside the square root. Close the parentheses for the log. Close parentheses for everything. And everything raised to the power of minus 2. Okay. Enter. See, click enter. You get it? See? 0.00680474. How close is the quiz going to be right here? It's a little different. A little different. Okay. Who else needs help? Oh, is that programmable one? Come here. Who else other than him? It's okay. I want to make sure that all of you can do this fixed point iteration calculation. Alright? Doesn't work. What did you put previously on this screen? Nothing? Oh, you have it already, right? Okay. It may be faster. Now how do I delete everything? Clear? Okay. First step, put 0.01. Enter. That is our initial guess, right? Then we put parentheses minus 4. Multiply. Log base 10. That's log base 10. Log base 10. Epsilon 150. Where's your E? Capital E. Oh, you don't have capital E. Maybe you want to buy a new one. Let's say capital E. Wait, oh, you don't have capital E. Oh, okay, you have this. It's over here. Okay, you see? That button is equivalent to capital E. 10 to minus 6, right? Go out of, you have to go out of the superscript. Okay, divided by 0.052 divided by what? 3.7 plus 1.256 divided by Renault number 1E5, right? Okay, go out of the superscript divided by square root F. Where's the square root? Square root answer. Square root answer. Go out of that square root thing, close parenthesis. That close parenthesis is for the log. And close parenthesis for everything. Then raise to the power of minus 2. Press enter. Get the number. Write it down. Press enter again. Get the seems to be wrong. Sadly, it doesn't work. Who have two calculators? No one have two calculators?
Use my phone.
Did I do anything wrong? I think I can do it, right?
You divided by the square root instead of multiply.
Oh, is that what I did? 150 e minus 6 divided by 0.52 minus 0.37 plus divided by. Oh, I think your computer is not E. Where's the delete? Where's the delete? Deleted one. Oh. Then row 5. Okay, now it's better. Now it's correct. So for this model, who use this model? Texas Instrument. Texas Instrument TI-30XS. Sell it, okay? I don't think it's good. Okay. So the problem that I have with this one is Renault number. Okay. In Renault number, how do I move over there? Enter. No, I want to see what I type. Okay. In Renault number, typically when I do 1E5, it considers this 1E5 as a whole term. But this time I have to do 1.256 divided by 1. Actually, you don't need to divide it by 1 and divided by 10 to the power 5. I put multiply over there. Okay. Now you're ready for the quiz. Good. Press exe one more time. Don't delete that. Okay. Are you ready? Okay. Everyone can do it, right? So the successive method is this. Maybe I just give everyone 10 points. You can do it. So the successive. No. Maybe. So we have to. The successive method is this. Oh. We have the equation. Okay. Let me draw my line first. How successive method work? Okay, I have this, and I also have x equal to some function, right? The right hand side. So this is y value, x is value. So what I do is y value, x value. If I plot y equal to x, I get 45-degree line, right? I get 45-degree line. Okay. If I plot just this function fx, that thing, probably it may do something like this. Okay, and we need to find a cross point. That is a cross point, right? So this method equivalent to we put the initial guess on y equal to x on this 45-degree line. We put the initial guess. Okay, based on this initial guess, we take it as input for fx, right? Input for fx. So we move this way. Okay, and then, oh, by the way, if the function look like this, it doesn't work actually. So the function may have to look like this. So I have the initial guess, fx. And based on that fx, I put it as an input for my function. So then this means that's the input, right, on the x-axis. Can you see that? Oh, I didn't zoom in enough. Oh, maybe that's too much. So that's the input function for fx, for the red line. Based on that input, I get that as an output, right? That is a new output. Based on that output, I take it as a new x. So I move this way. Okay? And it's like, did I do something wrong? This case is divert. Maybe the previous line looked good already. So from this we have, basically what you did is you go like this and until you reach the answer. So it is not always converge, but for the case of friction factor, yes, it converge. Okay. If the initial guess is too far away, it doesn't work. Okay. The initial guess has to be close enough. All right. Let's continue. And the last 5 minutes or 10 minutes, we will have the quiz. Or if I forget, we have the quiz next time. Are you ready just for this time? Just this time. Okay, single phase pressure of calculation, we talk about it a little bit. This case is about the equation that you see. It works for every case. Okay. It works for every case. Turbulent, laminar, gas, or liquid. It works for all. But we don't like it for gas case. Because for gas, when we flow, there's a change of temperature, right? So look at this one. There's a change of pressure and then density change, right? So this density change. If there's a lot of change, we have to discretize. So you did the homework, right? And you discretize it. What do you feel? You feel good about that? Or is a lot of work to do? Is it a lot of work to do, Stephen? A lot of work, right? So we have to have an easier equation. But first we will this part. Rho g sine theta or something. What is that theta? Who's the next? Adina, did you answer it? Oh, you're the next?
Yes.
What's your name? Mobile?
Yes, sir.
What is that theta? Angle from deviated from the horizontal line or from the vertical line?
Horizontal line.
From the horizontal line, correct. Okay, next, behind you, what's your name? Behind Mobile, what's your name?
Olivia.
What?
Olivia.
Olivia. So Olivia, from this equation, you see that F, friction factor, is that Moody or Fanning?
Got it.
What about capital D? ID or OD? Inner diameter or outer diameter?
Say ID, I guess.
What?
ID.
ID. Very good. Okay. So that tau is wall shear stress at the wall. Okay. So we go over all this a little bit. Okay. Something that I want to add into this slide is for the case of oil flow, most of the time accelerational pressure loss is very small, like when you do in the homework, right? Okay. dPdZ sub A, that term has to do with the change in velocity. Most of the case is small, it's negligible. The case that where it's not negligible is when we have flow in a well, vertical section, where the pressure is less than 100 psi. Okay? Just so you know. So if we flow in a well with a pressure less than 100 psi, pressure is low, right? The change of pressure causes a lot of expansion. But think about we flow at 2000 psi. Okay? 2000 psi. High pressure in the well, 2000 psi. There's a pressure drop from 2000 to 1900, 100 psi drop. But the gas doesn't expand much. Okay? So we will see the impact of acceleration of pressure loss for the flow in the vertical section, especially where the pressure is less than 100 psi. Okay? Good? Okay, next. Okay, most of the time when we have horizontal flow, the one that dominates everything is frictional pressure loss. Okay, frictional pressure loss dominates everything. The acceleration of pressure loss due to valve or choke or elbow or something is not that much for the long pipe. Okay. All right. Friction factor to use. Most of the time, if we do it at home, we can use Colebrook equation. Okay, the iterative process that you use, or we can use Gold-Sig. Okay. Or use Newton-Raphson. Newton-Raphson is the approximation of the next value based on the current point and the slope. Okay, it's faster. It's like 10 times faster than the iterative method. It's not in the exam. It's just so you know that it's a lot faster. Most of the mistake is not about you don't know how to do iterative method. It's about when it is laminar flow, you use turbulent flow formula. That is wrong. Okay? When it's laminar flow, has to use laminar flow formula. Okay. And the top part, even though the equation look very easy, it's good. It is a quick check if your answer is in the same order of magnitude or not. Let's say we have turbulent flow. We have 0.046 times random number to the power of minus 0.2. That is for the case of smooth pipe. Any friction factor that you get, it should be more than that for the case of rough pipe. Okay, and this is what we just did. This is important enough for us to spend like 20 minutes and make sure that everyone can do it. Okay. This technique is not only for solving the friction factor equation. It can be used for any kind of implicit equations when we have unknown on both sides. Got it? So it's quite powerful and it can be done on your calculator. Okay. Next one. Okay. Let's do gas pipeline. We are going to derive the isothermal flow equation for the gas pipeline. We need the equation because gas density is a function of temperature. Okay. We have pressure drop along the pipe and it causes the expansion of the gas. When gas expands, we can have Joule-Thomson cooling, right? Pressure drop when gas expands. So this means if we use this equation, it is correct. But what we end up doing is, like in the quiz, or like in the homework, we calculate pressure drop first. After we calculate pressure drop, we have to calculate what is the temperature drop, right? Due to Joule-Thomson expansion. Look at the Euler diagram. After we know the temperature drop, pressure drop, so we get the pressure and temperature at the next point, we go back and iterate it again. And again, until it converges. So in the homework, you iterate just for the case of pressure, right? But when you have to iterate until temperature converges to, it's not fun. Right? It's not fun. So it's complicated because there's a temperature change. Okay? Temperature drop can change the density. So everything kind of coupled together. In gas pipeline, there's enough surface for heat to transfer between gas and environment. If it is not insulated, then the heat can be added into the system. Okay, I have a pipeline. If I buried it, so it is perfectly insulated, then there's no worry about the chain of heat in or heat out, right? But if we do that, if we perfect insulation means this. If we had a temperature drop, temperature will drop. It doesn't get any more heat from the outside. Okay, we cannot assume isothermal flow for perfect insulation. If we have no insulation at all, we may just assume the gas in the pipe temperature equal to the ambient temperature, okay, equal to environment temperature, and it may be just isothermal flow. Any cold spot that it created, heat from outside will go in because we didn't insulate it. So it can be isothermal flow. Okay. So you can see the temperature has something to do with these two. Then we need a simplified form. If we use computer, we can discretize and calculate in a small section, assume the fluid property in each section is constant and do the integration. Or we can use some kind of numerical method to solve it. Okay. We don't do that. Okay. We have a faster solution by using the gas equation. Okay. Before we can have a general formula for gas equation, we need to know how will format look like. You remember last time that we do the flow through a show equation? We kind of derive the general form first. After we know the form, then we can put in the unknown constant, right, to absorb any uncertainty that we have in it. Okay. For a long, uninsulated pipe, we can assume isothermal flow. Isothermal means Kirin, what was your name? Kiran? Karim. What is isothermal flow? What does it mean?
Constant temperature.
Constant temperature, okay. Correct. Given up, so we can do some kind of approximation. And that's it. Final equation, it looks just like that. That's field unit and SI unit. In field unit, we use PSI-A. Don't use PSI-G, okay? Area, feet square, density power mass per cubic foot, square. This has to be 3, okay, cubic foot. Correct it, please. WS, mass flow rate, power mass per second. Okay. F, capital F is fanning friction factor. In SI is meter kilogram and second. Put that in. So we have the relationship between mass flow rate, okay, mass flow rate in power per second, and pressure drop, right? So if I know the pressure at point 1, so if I know pressure at point 1, I know pressure at point 1, I know this one, I know the flow rate, okay, I know density at point 1, I can calculate pressure at point 2, okay, pressure at point 2 is the only unknown. What about F sub F? What is that friction factor? Is that the friction factor before the expansion, after the expansion, or in the middle or something? Let's take a look at the derivation. We start from mass balance steady state. Okay. D rho UA equal to 0. That U is velocity, rho is density, A is area. By doing that, we get the change of mass flow rate equal to 0. Okay. So D is, later on we will change to D by dx. So we say mass in equal to mass out at any location. Okay. Take the D operator, operate it on each term, we get 1 over rho, d rho, plus 1 over u du, plus 1 over a dA equal to 0. Okay. For the constant flow area, dA equal to 0, so that term is gone, right? And we change from d to d by dx, we have that equation. Okay, that's the equation that we start from. 1 over rho, d rho by dx, plus whatever u du by dx equal to 0. That is just mass balance. Where's Rohan? You don't want to sit over there anymore? You can see the screen? Oh, okay, it's big there. Isothermal flow. We can use equation of state. PV equal to Z nRT. Okay? N is mass divided by molecular weight. So this gives me mole, right? I take the derivative. Okay, dP is d of that whole term multiplied by 1 over p on both sides. Okay, so I get dP over p equal to that term over that. Molecular weight is constant. Okay, we assume no change of the composition with the length. Okay, so I get d0 t over z rho t. Expanded, I get that. dt over t plus d rho over rho plus dz over z. For isothermal flow, there's no change of temperature, right? dt equal to 0. There's no change of compressibility factor. dz equal to z equal to 1 all the time, so dz equal to 0. So I get the change of pressure over pressure equal to the change of density over density itself. So this means density just changed because of pressure, not because of compressibility factor or because of any temperature. Alright? So that's the first step in derivation. Then we go back to the thermodynamic. Okay? Delta U plus, anyone else? Okay, we seem like we have everyone. So we have delta U equal to Q minus W. So that is for first law of thermodynamics, when there is no mass in or mass out from the system. For the case where we have mass in or mass out, we have those terms, right? And H equal to U plus PV, put it in. We combine that term and that term. Okay. No compressor work done on the system equal to 0. So W is 0. Horizontal pipe. Delta mgz equal to 0. So we have just that. Okay. Delta H plus delta 1/2 m u square equal to Q. Alright. Now we try to go a little bit more for the expression of the enthalpy H. Specific enthalpy can be written as this. A small change of specific enthalpy, we have this kind of equation, okay? dV V hat by dt, so hat is the property per unit mass. For the case of ideal gas, V hat equal to T dV hat by dt at constant P. So that term go to 0 for the case of ideal gas. Then the change of, and for isothermal flow, dt, the change of temperature is 0. So we don't have any change in enthalpy. Okay? Now we have the equation reduced to just the change of kinetic energy is because of the heat, just that. So this is, we take the derivative form, d form, we get u du equal to dq hat. Okay? And from mechanical energy balance that we already have, that you did in your homework, we have this, right? Delta, this is mechanical energy balance per density. Okay, is it per density? Yes, that's it's not per density because I multiply by mass flow rate. Okay, this is another form of mechanical energy balance. We have loss due to friction and compression term. Compression term is new one. You don't see this in your liquid equation. It can be expressed as, okay, minus integration of P divergent u dv. Okay, that is like the vector form, consider all direction. But basically, when we do the math, we will end up just this. Okay. Let me delete everything first. So what I have is that equation, and from no compressor, horizontal flow, with E sub c approximation, we have that equation. So E sub c approximation is about, do this approximation to be P divergent, is that divergent? Yes, divergent U dV. We have delta P over delta rho M plus E sub V, and approximate to be just that. Okay. No proof for this, but basically we can approximate the compression term like that. Okay, compression term can be approximate like that. We put it in there, do some more math, and a lot more math. Then we have that this equation. Combine mass balance, mechanical energy balance, everything in the D form. Use equation of state. Use continuity equation. Multiply continuity equation by U square. Pretty boring, right? When you follow it all the way through, and we do some kind of change. At the end, okay, rho u equal to constant. I know that you can read that. Do some more math. Okay, do integration. I don't worry that you cannot do integration or anything, but sometimes you just need to know some easy thing like that. Integration of 1 over p dp is log p2 over p1. You can do this, can you? Okay, so in the exam, if I just ask just that, it's a fair, right? I cannot ask for the whole derivation because it's too long. Okay, so once we combine our equation together, we integrate it, then eventually we cannot get that form. Okay, I rearrange it, I get the form the same as isothermal flow equation. Okay, now friction factor. Maybe I skip too fast. Where does the friction factor come from? The friction factor come from that part, right? That's where we have friction factor. Okay, let's go back about friction factor. So that is the friction factor over the length of dx. Good. So this is a friction factor defined based on the average Reynolds number in that section, right? This comes from like all this equation, right? So that is a friction factor that is between point 1 and point 2. It is not friction factor at point 1, it's not friction factor at point 2, it's a one average. Got it? Okay. From the derivation, that friction factor is the average. Okay, between point 1 and point 2. Question? No question?